and I am here today to present to you over the sustainability study of manufacturing of monosilicon photovoltaic solar panels. The goal of this study is to determine if the carbon emitted during the manufacturing of these solar panels outweighs the the energy and the carbon that is saved during the lifetime use of these same solar panels. And at Burns and McDonnell, it is our mission and our goal to make sure to see our clients be successful. And in order to do that, one of my jobs is to offer our clients the energy options and energy generation options that are going to be the most reliable, efficient, and sustainable for their large campus needs. And so in order to do this, there is a lack of understanding and a lack of research done over the entire life cycle and the global footprint that these solar panels have from their manufacturing. And so the two things that I'll be going over today are going to be number one, the structure, so that we can get a large idea and a large view of the solar panel structure and each component that goes into that, along with their associated manufacturing processes and how that affects the carbon emission. And then second of all, we'll be going into specifically the solar cell portion within the solar panel, which makes up the largest amount of the carbon emission, and so going into that manufacturing process and what that looks like as well. So to begin, we're going to be taking a look at the structure as a whole of the solar panel in order to get a better understanding of all of the elements that comprise it. The first of which is the aluminum frame, and this is responsible for maintaining the structural integrity of the solar panel and allow it to be mounted and to be able to hold everything, all of these components in place beneath it. Next, we have the glass portion, and this is a crucial part of the cell, and it also is one of another intensive manufacturing process that is often not talked about or is under-researched in contribution to the entire solar panel. But this glass is important because it protects the solar cells themselves, which is the aspect that is actually generating the electricity. I'll get to that in a moment. But the glass provides protection from the weather, protection during transportation from thermal shock. It needs to be able to withstand a variety of climates depending on where the solar panel is implemented. And according to the IEC, the glass must be able to endure a 1-inch diameter piece of hail traveling at 60 miles per hour without any breakage. And this is just to ensure that the solar panel itself is not damaged and that it can continue working. Next up, of the main components, we have the balance of system components, which within it comprises the encapsulant EVA, the backsheet, and the junction box. And these balance of system materials are there in order to maintain and to convert the electricity that is being generated within the solar cells and to send that out and disperse that to the rest of the facility for actual use. And the final component that I'll be discussing, and hence most important, is the solar cell itself. And in this case, we're studying the monosilicon solar cell. And this contributes one of its role is to actually undergo the photovoltaic effect, which, as many of you know, is the conversion of sunlight energy into electricity. And so this kind of brings me to seeing how this carbon emission from each of these processes is distributed. And as you can see, the balance of system components I spoke about before make up about 19% of the total carbon emission that is produced from this entire manufacturing process. But the PV or the photovoltaic module itself, that entire manufacturing makes up the majority of the carbon that is being emitted. And within this module manufacturing, you can see that the monocrystalline silicon production itself has the highest contribution of carbon emission in this process, ranging at about 1,500 kilograms of carbon dioxide per meter squared. Compared to the rest of the system, such as the aluminum frame, which makes up about 120 kilograms of carbon dioxide per meter squared, and the glass manufacturer, which is 160 kilograms of carbon dioxide per meter squared. It is clear to see that the actual cell itself has the highest contribution. And realizing that this aspect itself is the highest contribution, leads me to the next point, which is looking closer at this manufacturing process itself and getting a better understanding of what that looks like. So the manufacture of the monosilicon has the highest carbon emission as previously stated. But why is this? This is because in order to get this monocrystalline pure silicon, it first must start out as silica sand in its raw state. From there, it is put into a furnace and heated up and refined to about 99% silicon, 99% pure silicon, which requires a great energy input and also releases CO2 within that chemical process. From there, it is further refined to get a close to 100% pure silicon, crystalline silicon. And then from that point, it must further undergo a process that creates it into this monocrystalline ignot, which from there, once having the ignot, it must be sliced into very thin wafers that are actually used within the cells. But during the slicing process, there's up to a 50% material loss. So not only is there energy, this intense energy input, but there's also a physical material loss associated with this as well. And then finally, there's further processing done to the silicon wafer in order for it to be able to be put into our solar panels and act as a solar cell. So just to summarize and to wrap up, the two main points looked at within this talk today was the overall structure of the solar panel and specifically the components that go within that and their purpose within the solar panel. Then looking further at the carbon emissions related with each process, it was seen that the monosilicon solar cell itself had the highest carbon emission, and that was our point number 2, going into that process and why that process is so energy intensive and releases the most carbon dioxide. So to conclude, through this entire research process, being able to track the energy input and then the energy efficiency of the solar panels ranging from about 15 to 20% efficiency, it can be seen that the energy payback time, or the time for the solar panel to produce the energy that was consumed during manufacture and to, in a way, save that or repay that carbon, is about 4.5 years. And if a life cycle of the lifetime of a solar panel is roughly 25 to 30 years, that means that there is still viable and clean energy usage from these solar panels of about 20 to 25 years. And so, therefore, it can be concluded that these are still a viable and a clean energy option, but it must be considered that it's not 100% clean. There's still going to be a carbon footprint, and in those locations where these solar panels are being manufactured, that footprint increases, and that needs to be taken into consideration. Going forth, there are still a few aspects of the solar panel life cycle that need to be further researched and studied, and that were out of the scope of this research. That of which would be the disposal and recycling process and how that contributes to the carbon emission, and also the transportation and how transportation from often these manufacturer locations are in China or Taiwan or Malaysia, and how that transportation affects the total carbon emission that is released during the solar panel's lifetime. So those were a few of my conclusions and recommendations going forward to better understand um, how these can truly become a clean and renewable and sustainable option.